Hello everybody. It's a pity that we cannot meet in person in Vienna, so I hope it's possible again next year. So I would like to present you a recent work of my team and myself that we published in JGR. It's about deriving a CME volume and density using image data, so from remote sensing data, and then use that information to gain insight on sheath formation processes in interplanetary space as the CME propagates from Sun to Earth, and also insight or information about mass exchange between the flux rope and the solar wind. So first of all, we start with the derivation of the CME volume. You see here a very well-known technique, a 3D reconstruction using the GCS model, the graduated cylindrical shell model developed by Ternesier and collaborators. So it's an idealized flux rope that is fitted to white light data from different perspectives, stereo B, SOHO and stereo A. And on the right hand side you see this idealized flux rope geometry separated into several segments, and using that you can then calculate the volume. The algorithm is described in Holzknecht and collaborators in 2018, and it only uses the angular half-width of the GCS model and the kappa. So angular half-width alpha and kappa, the aspect ratio, are the two parameters that you need to know to derive the volume. To derive the CME mass, we use the total mass, also applying a multi-spacecraft information from stereo. The total mass derivation is described in the paper by Colanino and Voulidas and Bein and collaborators. As we have now our volume and mass at about 15 solar radii, we can use the assumption of self-similar expansion and first of all constant mass, and get the CME density over distances very close to the Sun, so 15 to 30 solar radii. So applying these methods on 29 CME events that were well observed, we derive the mean density of the CME or of these of the sample and standard deviation. And in comparison, we give the Leblanc solar wind model for the density. And from that we derive that we have at about 15 solar radii a ratio between CME density, so an average density, and solar wind density of a factor of about 11, and at 30 solar radii of a factor of 6. The list or parameters for all the 29 events are given in the JGR paper, and yeah, with that you can get yourself these calculations done. Yeah, in the next step we again, assuming self-similar expansion, we expand the CME to L1 so that we can compare the density to in-situ measurements. And we do that separately for the sheath structure and the magnetic ejector structure. So here is seen a schematic view, the CME as it expands and then sweeps over the spacecraft, and then we see the, for an example event, the sheath structure and the magnetic ejector structure. So from that we derive an average density, and that we can compare to our calculations. So we now use separate volumes for the ICME structures, sheath and magnetic ejector. And you see here the sheath structure and the magnetic ejector structure. So this is the full volume as it is derived from the GCS model, and we reduce the volume in order to mimic the CME geometry after propagation in interplanetary space. For the sheath, we do a similar approach. We have here the frontal shell only from the GCS model, and then reduce the volume to mimic a pile-up of material at the CME front. Using these reduced volumes and the mass that we derived, we then compare that to in-situ measurements. So I would like to note that the mass that we derived is most probably or most likely mass that is inside the flux rope, so the deprojected mass, and for the sheath region we use a separate mass that was already so it's already observed De Forest, for example, or also Lugas showed in simulations that the sheath region needs to be treated as an extra mass. So we now compare the derived model values to the in situ measurements. We see here box plots for the sheath region and the magnetic ejector region, assuming self-similar expansion and different expansion factors. And we play with the multiples of the mass, of the deprojected mass that is observed. So the difference between calculated and observed values is given here as zero line, so zero difference would be perfect match. And the box plots show the median value and low and upper quartile for the 29 events that we used. So on the left hand side for the sheath region, so this is half the mass of the deprojected mass that is used as extra mass for the sheath, so that's the piled up mass. That's the same mass, so a similar amount of mass would have been piled up in interplanetary space, and 1.5 times the deprojected mass would be piled up. And we see here that first of all we get rather low correlations, so 0.26 roughly, and we increase, so increasing the mass pileup, we come closer to the zero difference. However, also the spread in the results is getting larger. On the other hand, for the magnetic ejector region, we assume here 75% of the observed deprojected mass at 15 solar radii, so that would mean a mass loss of 25% roughly. That's the mass stays constant in the flux rope, and there is a mass increase of about 25% in interplanetary space. And we see here, or we derive that the magnetic ejector structure has a higher correlation, much higher correlation between 0.56 and 0.59. And also we come closer with the median value to the zero line, and also the spread. So, for example, using here these the results for a rather constant mass, self-similar expansion with expansion factor 1 gives a rather low spread, and very close to the zero line, the results. In the next step, we compare now the pre-event parameters, so the solar wind parameters ahead of the CME, and these are now only measurements. So there are no model values in. So we just have a look, especially for the sheath region. What are the parameters? Are there any relations between the solar wind characteristics ahead of the CME and the sheath density or the magnetic ejected density? On the right hand side we see the results for the magnetic ejector, and on the left hand side for the sheath. Interestingly, the sheath region now shows a very high correlation with the pre-event density, so that's 0.56, and with the pre-event speed. It's an anti-correlation, a very strong anti-correlation of -0.73. For the magnetic ejector region, on the other hand, the correlations are very, very low. We also see the bubbles here mark the transit times of CMEs, and we also see that that there is no systematics between fast or slow CMEs. So obviously there is no relation how long a CME propagates in interplanetary space and the sheath density that is then measured in situ. So with that can come to the conclusions. So we are able, with the algorithms that we use to calculate the volume of a CME, we can calculate the mass of the CME, and from that we derive the density. That gives rather nice results when compared to in situ measurements. So using this as a function of distance, we also hope that in future for Parker's solar probe, for example, to get also results for many more different distance ranges. We also find that the magnetic ejector structure, it covers the major part of the CME mass, and as as we measure from remote sensing data. So also the flux rope reconstruction and the mass within is obviously the mass within the flux rope. So the conservation of mass is a good assumption to derive a good match between with the observed density values, and also self-similar expansion is a rather plausible scenario. On the other hand, the CME sheath region, it forms and consists of piled up material in interplanetary space. So it's made up of solar wind material, and we do not derive nice matches just using this simple approach of mimicking the CME frontal shape with these idealized geometries that we have used. So it's a much more complex structure, and the amount of mass, the piled up mass, it is depending on the pre-event density and especially the speed ahead of the CME, but it is not depending on the CME transit time. And we also found, which is not shown in the presentation here, but you can read it in the paper, that wider CMEs, they tend to have larger sheath densities because of a piston type pileup scenario compared to narrower CMEs that act more like a bow shock. I hope I could raise interest in reading the paper, and yeah, take a look at the link that is given here, and thanks for your attention. Bye bye.